Good afternoon, everyone. For elastic wave field tomography, we can invert for multi-parameters. For example, we can invert for the velocity of P, the compressional wave, and S, the shear waves. Here is an example. There are two Gaussian anomalies in the P model, and as well as in the S model. Because of the problem of acquisition and noise, most of the time we are not able to resolve the models completely through inversion. So we are able, for example, we might get a P model showing in the right panel, in the second panel, where we are able only to resolve the Gaussian anomalies on top. And because of the difference in illumination and amplitude of P and S waves, we might get S wave, or we can get obtain inverted S model, which only has the bottom Gaussian anomaly resolved. So by comparing the resolved P model and S model, we notice that they are inconsistent with each other. So today, through the presentation, I will propose several modifications to the wave field tomography. And with those modifications, we are able to obtain a better updated P and S velocity models. And one of the most important modifications we propose is to enforce the physical relationship of VP and VS into inversion, and such that we can obtain the P and S velocity models which are more consistent with each other and more physically realistic. This shares a similar idea with Hui presented the research that Hui presented earlier today. Okay, so with the modifications, we are able to get the P models, which is showing the right panel, where both of the Gaussian anomalies are better resolved, as well as the S model. Let's go through the details of our modification. We consider the simplest elastic isotropic wave equation. This assumes slow-varying material properties. There are three model parameters: the density and the lambda and mu are Lamé parameters. We can rewrite the equation and reduce the number of parameters from 3 to 2, and we use alpha and beta instead here. So here, alpha is the squared velocity of P wave, and the beta is the squared velocity of S wave. And through our presentation, we will show the inversion using alpha and beta. For model optimization, we typically minimize the objective function to update the model. We consider an objective function containing three terms. The first term, JD, is a data term, which quantifies the data misfit. And the second term, JM, is a regularization term. It contains individual prior information of alpha and beta, as well as model shaping. And we introduce a third term into the objective function, which is a constraint term. Using this term, we want to constrain the relationship of alpha and beta within a feasible region. Okay, so for the first term is a data misfit term. And this term has been widely used by itself. This term quantifies the difference between observed data, DO, and predicted data, DP. So we choose to use gradient descent method to iteratively update our model. And the efficient way to compute the gradient is the adjoint state method. And using the adjoint state method, we are able to compute the gradient for alpha and beta shown in this slide. Here, the star denotes the zero-lag cross-correlation, and the sum over E means we sum the gradient from each experiment together. And here, notice that U is the state variable, which is the wave field computed using an estimated source wavelet. and A is the adjoint variable, which is computed using an adjoint source. Notice that in the gradient for alpha, there was a divergence of u, which comes out naturally from the equation. From Helmholtz decomposition, we notice that this is the p wave of the displacement wave field. And in the second term, the gradient for beta, there is a curl of the displacement wave field, which is the S wave only. Through the presentation, I will use a very simple model for illustration and to see how we compute the gradient as well as the inverted models. The model is very simple, contains one Gaussian anomaly in the center in both alpha model and beta model. The acquisition geometry contains one source, which is indicated by the blue dot, and one receiver, which is indicated by the red dot. And now there are 3 panels from top to bottom are showing the observed data using the given geometry and the predicted data and the difference between them. And we are recording 2 components of the data. The horizontal component, which is denoted by the blue dashed curve, and the vertical component, which is denoted by the red line. Notice that there are 2 arrivals in the data. The first arrival is the P wave, and the second arrival is the S wave. And now we use the data misfit, which is the bottom panel, as the adjoint source to generate the adjoint variable, the wave field. Because there are two arrivals in the wave field, and we generate them back as displacement source. Both of the arrivals will generate P and S waves in the wave field. Here are the P and S waves generated by the P wave in the adjoint source, and followed by the P and another group of P and S waves generated by the S wave in the recorded data. And then we use and notice that there are 2 P and S waves which are highlighted by the yellow box, which are the cross terms. And when we apply the equation to compute the gradient, they will cross-correlate with the P and S modes in the source wave in the state variable, and then generate artifacts in the gradient. By applying the equation, and we obtain a gradient shown here. They are plotted in the same scale, and the left panel is a gradient for alpha, and the right panel is a gradient for beta. And we notice that the blue color connecting the source and the receiver locations are shown for model updating. Addition to that, there are higher frequency events spreading out from source and receiver locations, which are caused by the events by the cross terms that were shown in the wave field. And there are several problems of the gradients. First one is since the 2 gradients are plotted in the same scale, and we notice that for this specific case, the gradient for beta is much stronger than alpha. This is because in our recorded data, the S wave has higher amplitude than P wave. If we use the same step lengths for model updates, the beta model will have a better resolution than the alpha model. And another problem of this gradient is the gradient is not uniformly distributed. We notice a very high value at source and receiver locations and a relatively lower value in other spatial locations. So we're going to propose several modifications to the elastic wavefield tomography to improve the gradient and able to get better inverted models. The first thing we applied was to trying to balance the energy of the gradient to make it more uniform. So this is the equation we've shown to compute the gradient. Now we take the L2 norm of the terms for cross correlation and put them in the denominator. Using this illumination decomposition, we're able to get the gradient for alpha and the beta, which are more uniform. Now, these two gradients are plotted in the same scale, and we notice that the gradient for beta is still much stronger than alpha. So we propose the second modification, which is to balance the parameters. In this equation, the alpha and the beta stands for the velocity of P and S, squared of P and S velocities respectively, and the value of alpha is generally much higher than beta. So we modify the equation to introduce a scaling factor C into the equation. So with the C, and the value of alpha and beta could be comparable. And now we're still inverting for parameter alpha and beta, and with the introduction of scaling factor, we're able to get the gradients for alpha and beta which are more comparative in values. And with this gradient, we can use the same step lengths to update both alpha model and the beta model. And now we start doing modifications to the objective function. As we mentioned before, we introduce a second term into the objective function, which is the regularization term. This term contains the prior information of individual alpha and beta models, which are denoted as alpha bar and beta bar. The weighting matrix W alpha and W beta are inverse model covariance. We can introduce model smoothing and image guiding to the matrices. And there have been a lot of discussion about this term. And today we are not going to further discussion into this term. And for the last modification we propose is to introduce the physical constraint into inversion. Here are some dots, some values of alpha and beta are took from the elastic Marmousi model. The horizontal axis is the value of alpha and the vertical axis is beta. So notice that most of the alpha and most of the points can be defined within the range. So we call this range the upper boundary HL and the lower boundary HU and the lower boundary HL. Notice that I'm drawing two lines in this case, but in general, these two boundaries can be curves with arbitrary shapes. So through our inversion, we want to constrain the model updating, staying within the boundaries. So, and we want to form these two inequalities into our objective function. The way we choose to implement that is to put the two boundaries into the logarithmic format. And here the parameter eta is a weighting parameter which balances the contribution of the constraint term and the rest of the two terms. So with the characteristics of the logarithmic function, once some samples in the model approaches either the upper boundary or the lower boundary, the value of the objective function will dramatically increase, and the corresponding gradient will try to push the model back away from the boundaries. Go back to the model. By setting a proper upper boundary and a lower boundary, we can compute the gradient from this constraint term, which is shown here. In the gradient, we observe that the gradient for alpha and beta appear with opposite sign. This means this constraint term is trying to decrease the value of one parameter while increasing the value of the other parameter, such that their relationship is physically realistic. Now I'm going to show you some inversion results with the same model, and we increase the number of sources and number of receivers to obtain a better illumination. So the blue dot shown here is a source, and the red dots are the receivers. So for the inversion, I will compare the inversion results with constraint and without constraint. After a certain number of iterations, we look at the updated alpha and beta models. And here is the alpha model on the left. We can see the Gaussian anomaly in the middle, in the center of the model, and the panel on the right has the red curve, which shows the value of the updated model at the location indicated by the black line. And the blue dashed curve is the value taken from the true model as a reference. If we use the inversion, we look at the updated model with constraint, we can obtain an alpha model shown here. So without constraint and with constraint. And now we see that with constraints, we are able to obtain an alpha model which is closer to the true model. And this also happens to beta model. So beta model without constraint, with constraint. Again, we obtain a better beta model closer to the true model using constraints. Now we take a sample from the model and look at the model update through iterations. We plot the value all in the same figure. Again, the horizontal axis is the value of alpha, and the vertical axis the value of beta. The blue two lines are denoting the upper boundary and the lower boundaries. And the red line in between is the ratio of the true model. And the green dot on the right top corner is the value of the starting model, and the white dot on the left bottom panel is the corner is a true model. And now if we look at inversion without constraints, we see the model moves to starting from the green dot and move toward the true model. And for comparison, and we plot the inversion with constraints in the same figure, and we see that after both conversion both inversion converges, the inversion with constraints is closer to the true model, and it's closer as well to the true ratio of alpha and beta. Now let's go back to the model I've introduced earlier in the very beginning. This is a cross-wire example. It contains two Gaussian anomalies. On the left is the blue line is the source line, and the right and the magenta line is the receiver line. And these are two Gaussian anomalies also existing in the beta model. And for this inversion, we use we also use transmissions only for model updating. So here are the updated models. The X component, here are the recorded data, the X component and Z component. In the two components, we observe the P waves as well as the S waves. With this data, we are able to resolve both Gaussian anomalies in alpha and beta models. And so now we make the situation a little bit worse. We milled half of the data, only keep the P wave for the receivers at the depths from 0 to 3 kilometers, and keep the S waves in the receivers for the receivers at the depths from 3 to 6 kilometers. Now use this data. We only we use the data misfit as the objective function. We only resolve the Gaussian anomaly on top, and the Gaussian anomaly in the bottom in the beta model. Now if we use the physical constraint into the objective function, we are able to resolve both Gaussian anomalies in the alpha model as well as the beta model. Again, we take a sample in the model, which is the center of the top Gaussian anomaly, and look at the model updating, which is shown on the right. Again, the green dot shows the starting model and the white dot shows the true model. And now the blue dots are showing the model updating without constraints. We see that after iterations, the model moves towards the upper boundary, and which means that the updated model is not physically realistic. While with constraints, we're able to keep the alpha and the beta models away from both upper and lower boundaries, and they are physically realistic. To summarize my presentation today, we're introducing the elastic wavefield tomography, and we invert form parameters alpha and beta. We proposed several modifications to the tomography, and the most important one is to enforce the physical relationship of alpha and beta to the model updating. Before I end the talk, I would like to share some very fresh results we just got recently, and unluckily we are not able to include these figures into our project report. And here is an inverted model from a Marmousi. And we use a data misfit only to obtain the alpha model on the top and the beta model in the middle. And we take all the then we draw the cross plot of alpha and beta and plot from all the samples and plot them in the bottom panel. And here we see that the values of alpha and beta spreading out in the whole space. And for comparison, we also apply the inversion with constraint. And we see that the obtained alpha and beta model are more consistent with each other. And in the plot at the bottom, and we see that the alpha and beta are constrained away from the upper and lower boundaries. Thank you for your attention. I would like to take some questions.